Alright, so moving on, we're going to look at a type of interest that you see a bit more regularly than the simple interest we looked at last lesson. So I'm sure most of us have bank accounts, specifically savings accounts, and you may notice if you have a savings account that every month or so the bank gives you some interest. And the reason they do that is because your bank account gives you a certain interest rate, annual interest rate, that's compounded what we call monthly. And what that means, every month it gives you interest. But the nice thing about your bank account is that the interest it gives you also earns interest. So let's say you had $1,000 in there and you gain $50 in interest in 1 month. The next month, the interest is calculated based on that $1,050, not just the original 1,000 that you had in there in the first place. So that's the type of interest that you more commonly tend to see with loans and with investments. So the big thing is with compound interest is, again, your interest is earned on all the accumulated balance, not just the principal. So it's calculated on the not just principal, but everything that was earned on top of that as well. So what I want to look at is a situation where we have, just like we saw last lesson, an investment of $4,000, and the account's earning 3% a year, but instead of it being simple interest, it's going to be compounded what we call annually. So once a year they give you the interest. So to find our interest, basically what we're going to do is we're going to take $4,000, and we're going to earn 3% of that in interest in 1 year. So 4,000 times 0.03 gives us $120. So after 1 year, we add that $120 to the original 4,000, and we have a total investment value of $4,120. Now, for the next year, though, the interest is calculated not on the original 4,000, but on the 4,120. So for year 2, our interest is going to be 4,120 times 3%. And when we calculate that, we get $123.60. And now that's added on to the $4,120. So now we have a total investment value of $4,243.60. And you continue on doing that. So for 3 years, it's going to be this value times 3% added to the original, added to this value right here. And you can continue filling out the table right here. Now, what do you notice in terms of patterns in the table this time? Well, you may notice very, very quickly this isn't going to be linear like simple interest was. And what you may actually start noticing here, since again, it's not linear, you can check your first differences, you can check your second differences, it's not quadratic either. What you may notice after some experimentation is that you have what we call a common ratio. So meaning, if I were to divide these two values, so 4,243.6, and I divide that by 4,120, I get 1.03. Okay, if I take the value after year 3, 4,370.91, and I divide that by the value from year 2, I again get 1.03. And you can continue that pattern all the way down. So the big thing to notice here, since you have no constant differences, you have what you would instead call a constant ratio. And what unit do we see constant ratios in the periodic tables? Well, we saw them in exponential functions. So what this is saying is that compound interest follows the form of an exponential function. Okay, so which means it follows an exponential function. We have a formula that's actually going to be very, very similar, just an extension of the y equals c to the c times a to the x that we saw when we were with exponential functions last unit. And what the formula actually is a equals p times bracket 1 plus I to the n. Now I'll explain what all these formulas mean, what all these variables mean. But the one thing you'll notice here is you have some sort of starting value here, and then 1 plus I. Well, it's simpler if you have something growing, it's going to be 1 plus a growth rate, just like we had with the exponential function that we looked at last unit. So hopefully you see this as just a little bit of an extension of what we saw last unit. Now, as for what these variables actually mean, let's clear some space out of the way here. Some of these variables might look a little bit familiar from simple interest, and some of them should. So P is simply just going to be your principal. Okay, so that is, again, just the original investment or the original amount that was borrowed. Okay, A is going to be just the value of the investment, so the total value. And I should probably not just call it investment, because this could be a loan as well, so investment or debt, I should say. Okay, so after a certain amount of time, you'll have a principal that's going to grow to a certain amount that you either owe or that you've earned in terms of your investment plus your interest. So all that's left here is this I and this N. Now, I, we're going to have to talk a little bit more about on the next slide. So I is your interest rate. But it's not going to be the annual interest rate. It's going to be interest rate per compounding period. And I'll talk about what that means a little bit more shortly. So interest rate per compounding period. It's not just taking the annual interest rate, because interest can be compounded at much different rates. And when I say compounded, that means that when it's calculated and added to the total. So you can, in your bank account, you get interest every month. That means the interest rate is compounded monthly. You can have interest that's compounded weekly, annually, quarterly, bi-weekly. There's lots of different options. So we'll talk more how we can handle that in a second. And last but not least, N is the number of compounding periods. So again, it's the number of times the interest is calculated and added on to the investment. Okay, so P and A are relatively straightforward, right? It's your starting value and the total value of the investment or the debt. I and N is what can generally cause the most confusion when you're dealing with these types of problems. So one thing I will say, so let's just say we have an annual interest rate of 8%. So 8% per year. And let's just say it's compounded, we're going to say monthly, for example. Well, that doesn't mean they're giving you 8% interest every single month. That would be absolutely absurd. Your investment would grow way too much. What they actually do is they take this at 8% and they spread it over the 12 months that you have. Okay, so instead of 8% every month, you're going to have 8% divided by 12 given every month. Okay, so when you talk about the interest rate per compounding period, not just taking the annual interest rate, you're going to divide it by the number of times per year you get the interest. Okay, and for a number of compounding periods, again, let's just, using our example, let's just say it's 8% annual interest rate and it's compounded monthly. Well, let's just say we're compounded for a period of 4 years. Well, you're not given the interest 4 times, you're given the interest every month for 4 years, so it's going to be 4 times 12, so 48 times the interest is calculated and added onto the investment. So the interest is given to you, calculated 48 times over the course of 4 years, but you're not getting 8% of your investment every single time, you're getting 8% divided by 12 every single time. So again, this can be the part that can cause the most confusion when dealing with these types of problems. We're going to take a look at some examples on the next slide of how to specifically calculate I and N before we start doing a lot of problems. So with that in mind, let's take a look at that. So in these situations, I just want to look at what the values of I and N will be. Okay, so I'll do the first few with you together. So in the first case, it's a 17-year investment, and it's 6% per year compounded quarterly. So quarterly will mean 4 times per year. Okay, so let's just call this A, and I'll work on it down here. So for I, what you're going to do is you're going to take your annual interest rate, which is 6% per year. We're going to convert to a decimal like we always do with percentages. And since it's compounded quarterly, it's going to be 0.06 divided by 4. Okay, and this would be the value of I that you put in the equation. If it winds up reducing nicely, then you can reduce it. Or again, if the division turned out to be something nice, you can do that. So 0.06 divided by 4 is equal to 0.015. So 0.015 would be what you'd put in the equation for I. You wouldn't put in the 6%. Now, I will say that, again, this reduced quite nicely, 0.015. If it winds up being an ugly decimal, don't round, okay? Just leave it as a fraction inside the equation so you can keep the accuracy as long as you possibly can, okay? When you're dealing with exponential functions like we saw last year, if you round too early in the equation, it can lead to a lot of inaccuracy later on. So in this particular case, it's fine because it simplifies exactly, but if it doesn't, please leave it as a fraction. Now, as for N, what we're going to do is we have 17 years, but you're not given the interest 17 times, you're given it 4 times per year. So we're going to multiply that by 4. So the interest is compounded 68 times over the course of those 4 years. So the N that you're going to put in the equation is going to be 68. Okay? So again, you can't just blindly take numbers from the from the problem and just throw them into the equation, you have to make sure you're looking at the compounding rate and then adjusting the values for I and n accordingly. Okay, so I'll do B with you, and then I'm going to let you try C, D, and E on your own. Okay, so in B, 5 years at 10% per year compounded semi-annually. Okay, semi-annually will mean twice a year. So for I, we have 10%, which is 0.10. Twice per year, so divide 0.10 by 2, so you get 0.05. Okay, as for n, it's 5 years at twice a year, so you're going to put in 10 in the equation for n. Okay, so hopefully that makes a bit of sense. I'd like you to try the next 3 on your own, C, D, and E, and when you're ready to go through them together, push play, and we'll see how they go. Okay, let's quickly run through the answers for C, D, and E. With C, let's deal with the I value first. So again, it's 8% per year, so that's 0.08. Compounded monthly. Monthly is 12 times per year, so you go 0.08 divided by 12. Now, if you run that through your calculator, it's not an exact decimal. It's actually quite messy. So again, when you put that into the equation, please leave it as a fraction so you can preserve accuracy as long as you possibly can. As for the value of n, the trickiest part here is converting 3 years and 5 months to years. So 3 years plus 5 months is 3 plus 5 over 12, which when you simplify it gives you 41 over 12 years. Now, then again, you multiply that by the number of compounding periods per year, which in this case is 12. So 41 over 12 times 12 gives you 41. Alternatively, if you just convert everything to months, 3 years is 36 months. You have 41 months total, so 41 months compounded monthly will again be 41 times. So whichever way you want to look at that is fine, but both ways you wind up with an n value of 41 for the equation. Okay. For D, 15 months at 3.25% per year compounded weekly. So for I, you take the 3.25%, again you convert it to a decimal, then weekly is 52 times a year, so you divide 0.0325 by 52. Winds up being 0.000625, so it is exact, so you can leave it like that, or if you find it easy, you can leave it as a fraction. Either one is fine for that one. As for the n, you have to be a little bit careful here. What some of you may have done is you might have converted months to years by multiplying by 4, by saying there's 4 weeks in a month, and that's close, but it's not very accurate because it's really just an estimation. In fact, most months have more than 4 weeks in them because they have 30 or 31 days. So that's not quite accurate. So that if you'd done that, that would give an answer of n for 60, which wouldn't quite be right. So what you want to do is, again, convert months to years by going 15 divided by 12. So 15 divided by 12 years. Then you multiply that by 52 weeks in a year. So 15 divided by 12 times 52 gives you an n value of 65. Okay, and last but not least for E, we're compounded annually, so annually is just once a year. So if you ever see that, you're quite happy because you don't have to really do anything. The annual interest rate is just 0.045 and it's divided by 1, so it stays the same. As for the n value here, we just have to convert 6 years and 5 months to years. So 6 years is 6 years. 5 months is 5 over 12 years. Add those together, you get 77 over 12 years. Multiplied by 1, if you want to go through those motions, you can, and you get 77 over 12 for the value of n. Okay, and again, once you understand how to alter the values of I or n so they fit in with your situation, fit into the equation, you avoid where most of the mistakes for compound interest come from. Okay, so that was a lot of work doing setup before we could actually do a problem. So what I'll have you do is just try and set this one up based on the original equation that I gave you, the A equals P times 1 plus I to the n. Okay, so in this situation, it's $4,500 at 3% per year compounded quarterly, which you know is 4 times a year. We want to know how much we owe after 5 years and 4 months. So just try and set it up, and we'll run through this example together when we get to part 2 of the lesson.